All right. Well, thank you very much for the introduction, and thank you for the invitation to speak here. And it's a pleasure to be about to talk to you about this stuff. So I'm going to talk about factorization homology, as suggested by my title. And what I'd like to tell you about is what factorization homology is, and what it's supposed to be. So it's supposed to be an answer to the following question or problem: that of how to study multiplicative invariance by local to global methods. I.e., by some form of sheaf theory. So what do I mean by multiplicative? I mean invariant, which multiplicative refers to how this invariant behaves on disjoint unions. So one of the big themes of 20th century mathematics is how to study additive invariance by sheaf theory. So by an additive invariant, and the sort of 20th century analog of this story, would be one whose value on a disjoint union of two spaces or two manifolds is, well, if it's numerical, then given by the sum of the numbers associated with each of the components, or if it was valued in chain complexes or spectra or something like that, given by the direct sum, sort of depending on the categorical value of what this z is. And then, depending on if this was numbers or this was chain complexes, the way that the sorts of things that you'd ask for to understand about z in this sort of local to global approach is to try to understand this value z as being expressed in terms of some form of integration, which is natural to a given homology of some natural class. This is the sort of the meta theorem that you would then hope to achieve by use of some kind of a homology theory. Or to say, if in the first case, or that z itself was given by some kind of homology with coefficients, in some sense, with z of a point. So things which fit into this first example are things like the Gauss-Bonnet theorem or the Gauss-Bonnet-Chern theorem, that in the case where z is the Euler characteristic, there's a natural class, the Euler class, and the Euler characteristic is given in this local to global sense by integrating the Euler class. Likewise, Hirzebruch's signature theorem, the numerical invariant is the signature, and then there's a natural class, the L genus, and the signature is given by integrating the L genus for an oriented four-dimensional manifold. Likewise, the Atiyah-Singer index theorem fits into this sort of paradigm. Over here is the index of a Dirac operator, which is something which doesn't look local at all, the sort of difference, this difference of two dimensions. But then actually it does have a local expression integrating the A hat genus, and that can be expressed naturally in homology or K theory. Now, whether z can be expressed with homology of coefficients in z of a point, this is something which is given by the Eilenberg-Steenrod axioms, and what you need to do is you need to check whether that not only does z send disjoint unions to direct sums, but a stronger condition, namely excision. So these are the sorts of things that you might hope to carry over in some way to understanding multiplicative invariance, where now multiplicative means here that on a disjoint union of two spaces, that instead the value is, well, if they were numbers, the product of the two, or if they were in, say, chain complexes or spectra, then the direct sum or the wedge of the corresponding values. For that's being what multiplicative is. Thank you. I meant to write tensor product. And so I meant tensor product of chain complexes or smash product of spectra. Thank you very much. Okay, so that's the question I'd like to start with. Any questions before we move on to the answer? Okay, so here's an idea. It's not, here's an idea, and they never put it quite this way, but it's embedded in the work of Bellinson and Drinfeld. The idea is to use RAN spaces, RAN space, the space of finite non-empty ordered subsets. So some way of smashing together all the configuration spaces of a space. So first let's note that here, for additive invariance, you could just use sheaf theory on the space itself. And that's natural because if you have a sheaf valued in chain complexes, well, sheaves on disjoint unions send it to direct sum. So it's pretty natural that you could just consider sheaves on X or on the disjoint union. However, a sheaf on X or a sheaf on the disjoint union will never have property 2. So right away, if you want to use usual sheaf theory, you know that it can't take place on these spaces themselves. So an idea is, instead of considering sheaf theory on the space X or the space X disjoint union Y, instead construct some auxiliary space that has this sort of multiplicativity built into it. So that's what these RAN spaces are, and now I'll tell you what they are more precisely. So definition, just to fix our notation, the configuration space of I ordered points in a space X is ordered I tuples, all of which are distinct from one another. And that's topologized given the subspace topology of the Cartesian product. There's an action of the symmetric group on this, and the quotient is the unordered configuration space. So if X is a connected topological space, then the RAN space of X is, as a set, the union of the unordered configuration spaces. Starting at 1. So that's what the set of elements. So it's just another way of saying this is just as a set, it's the set of finite non-empty subsets of X. Now I haven't told you what the topology is. The most obvious topology might be just to make this a disjoint union, but that's not what I want. What I want is for points to be able to collide without, if 2 points, which are you think of as sitting inside the image of X to the 2, inside configuration space of 2 points, if they come together to form the same point, well, you think of it as leaving the stratum of conf 2 and going into the stratum of conf 1. And we want that procedure by which points can collide and cardinality of subsets can change to be continuous, reflected in the topology of RAN X. So what's that? So how to say what that topology is? Well, to say what that topology is, it's convenient to note that there are natural maps. So this will be continued in just a second as soon as I make an aside here. So note that there are natural maps X to the I. These are maps of sets to RAN X that send some I tuple to the image. As a subset of X. So in other words, if all of these were, for instance, the same point in X to the I, then the image would only consist of 1 point. And so you see that this map naturally maps to different of the configuration spaces. So this naturally maps to the subset for j less or equal to I of conf I of x sigma I. And it maps to the of conf j, depending on how many of these are distinct. So we have these naturally defined maps from Cartesian products to ran x. Call this, well, but I don't need a name. So such that these maps, this will be given the strongest slash finest topology. So in other words, fewest convergent sequences, such that these maps x to the I to the ran x are continuous. For all numbers I. Okay, so that describes what the topology is on ran x. Yes?
Is that equivalent to saying the map from the infinite symmetric product is a quotient map?
So it depends what you mean by the infinite symmetric product. So usually when people say that, they mean a pointed space, and there's no point here. So if by that you meant the disjoint union of the sim i's, then indeed it would be the same as saying that this is continuous, and it's natural that that maps through sim I of x. So it would be equivalent to saying that that map is, but you might have meant something different by the infinite symmetric product.
I was confused about what I meant. So
Everyone gets confused about this issue the first time. But x is not pointed, and this is not the infinite symmetric product of a pointed space as it arises in Dole-Tom theory. So where this arose, since we're talking history, I'll take an aside here. So I believe that this space, although Bellens and Drinfeld call it the Rahn space after Ziv Rahn, who began studying it, I think, in the late 80s or early 90s, roughly. This was originally called the infinite symmetric product. Before Dold and Tom, it was studied by Borsuk and Ulam, who in the 30s, who wrote a paper on it, and then there was a mistake of Borsuk, and Bott corrected that mistake in studying the Rahn space of the circle. But none of them had Bellens and Drinfeld's idea about what role in mathematics it was supposed to play along these lines. So, okay, so that's the Rahn space. Any other questions about the Rahn space?
What happens when x is disconnected?
Oh, good, good. Okay, so definition continued. We'll say that the Rahn space for x general, the Rahn space will require you to have one point in each connected component. So it'll be the subset of this, all the conf I x sigma I, such that there is at least such that Rahn of x contains a point in each component. Of x. So that's so when I was a graduate student and I said like topological space, and then someone else would say something like, you mean a pointed space or a connected space, that always struck me as the height of being pedantic, but now I'm that person. So this issue of being unpointed and whether it's connected or not are really essential. So let's note that since we got these definitions right, that this has the property that if you can take the Rahn space of a disjoint union, well, what's a finite non-empty subset of x disjoint union y? Well, it's 1 in x, and it's a finite subset in x, and a finite subset in y. And that's it. So clearly, this is the same thing as the Cartesian product of the Rahn space of x with the Rahn space of y. So the Rahn space, in other words, is behaving like an exponential space. It sends, so this is, think exponential, it's sending disjoint unions, which you could think of as being like plus to Cartesian products, which you could think about as being like multiplication. So that might give you a hint that sheaf theory on the Ron space might be a good idea for trying to understand things on X that satisfy multiplicativity, because it's no longer going to be the case that if you have a sheaf on the Ron space, its behavior on disjoint unions will force to be direct sum, since that, look at what it's doing with direct sums, sending it to products. So now let me tell you how factorization homology works. So what's the recipe for factorization homology? And all of this will be the what we call the alpha version. And that reminds me to say we, because everything I say is joint with David Ayala. And sometimes I forget to say that because I assume that everyone already knows that. And parts of it will be joint with Hiro Lee Tanaka and Nick Rosenblum also. So the recipe is the following. There are two inputs. So one of these inputs is geometric. And the dimension will be important, and so the dimension will always be n for the rest of today. And the other input will be algebraic. And what kind of algebraic data is required will depend at very least on the dimension, but also maybe on X and what kind of geometry we want to consider. I'll just say this depends at the very least on n and maybe also on X. So then, once we have these two inputs, there's a construction. Got to do something. So this construction produces, maybe I'll call it F sub A sheaf, or maybe it's a co-sheaf, or something like that, on the Ron space of X. And then we get factorization homology. So factorization homology of X with coefficients in M in A will be written with this integral sign, because we think of it as some categorical form of integration. And this will be equivalent to the homology or the chain level or wherever this is living of the Ron space of X with coefficients in this co-sheaf defined by A. So that's the recipe. So now what I'm going to do for the rest of today is sort of follow this recipe in a few interesting examples where the geometric structure varies, the dimension varies, the algebraic structure varies, and tell you what you get. But just, so I won't tell you in such a way to sort of, I'll tell it more of as a tour rather than an advertisement. But for advertisement purposes, let me just write over here that there are some advantages to doing this. And these advantages are of two types. So the one type is you could take something that you already know, and you could say that it comes as a result of this machinery. And then you could ask, so what? So these will be advantages of the first type. So taking something that you know and saying that it comes as a result of this, you get a form of excision, which we call tensor excision. Another thing is that if you take something you know, it might not have been expressed in terms of the Ron space, and the Ron space carries a filtration by cardinality. These are closed subspaces. If you just filter the Ron space by bounding all subsets of cardinality at most I, that gives you a filtration. And so at the level of homology, that gives you a filtration, that gives you a spectral sequence. So filtrations are powerful, spectral sequences are powerful, so you get that here. And then lastly, there's a kind of duality inherent to factorization homology, which might not have been apparent in the other thing that you were studying at all. And this is a simultaneous generalization of Poincare duality for manifolds and Cazul duality for algebras. And that potentially gives you something new. So the other kind of advantage to saying that something comes from factorization homology is maybe it was something that you wanted, but you didn't know how to define. And the other virtue that factorization homology has is that it's well defined. So these roughly are the things that you get. I won't talk about them too much in this little tour, but if at any point any of you are like, what was the application of one bullet 2 to one particular thing, just ask, and I'll tell you what it was good for, if it was good for anything. So that's a real invitation. Okay, so now the tour part. Any questions? Yes?
Two questions.
Two questions.
Yeah, really quick. Is it homotopy invariant?
No. Homotopy invariant in the manifold, you mean? Or in the geometric input?
For a space.
X, no. Not necessarily.
Okay, and the other question was, does the Ron space functor have an adjoint?
No.
Okay.
So the lack of an adjoint is kind of like how at the level of numbers you can exponentiate and you can take the log. And exponentiating is an operation of numbers which lifts. You can consider infinite symmetric powers. However, logarithms don't lift. So someone might have objected to this whole program to be like, hey, if you can study additive invariance by sheaf theory, why not just, exponentiate, or take your multiplicative invariant, take the log, and then study it this way. And the issue with that is that is exactly this sort of lack of a categorical logarithm. So if there was such a thing, then I think this whole program would not be a good idea.
What happens if you exponentiate an additive invariant?
So you got a multiplicative invariant, and that's the easy direction. Yeah. So there you're good. But there it's a little less compelling to tell someone who's got the Atiyah-Singer index theorem, well, that's great. We can do the same thing with the multiplicative form, you just have to do it infinitely many times. So. Okay, so our little tour. Maybe I'll keep track of the stops on our tour in this little box right here. So first is real dimension 1. So here, X is a 1 manifold. Now I need to tell you two things, what kind of geometric input there is and then what kind of algebraic input there is. The algebraic input A is an associative algebra. And now there's a construction which produces F sub A, a cosheaf, which on the Ron space of, well, whichever one manifold you wanted. This could have been the real line, this could have been the circle, or it could have been any finite disjoint union of the two of those but just for specificity, let's say on the real line. So the stock, so it's good to think about what a sheaf or a cosheaf is in terms of its stocks. The stock at an I tuple, an unordered I tuple, is A tensored with itself I times. And then so on each of these configuration space layers, you get a constant cosheaf. And then you could ask, how are these things glued together? Well, so this will be constructible with respect to that stratification of the Ron space. And so when you have a constructible thing, the thing to ask for is what happens as you change layers. In other words, if you choose a path into the Ron space, in which one point goes into a deeper stratum and the rest goes into a higher dimensional stratum, what is the associated specialization map from the generic fiber to the special fiber? So if you choose such a path, in other words, an exit path, to the, say, Ron space of R, it sends one point to, say, X, and other points to, everything else goes into the stratum with two X sub t, Y sub t, everywhere else. What do you get from, say, the generic fiber to the special fiber? Well, you need a map from A tensor with itself twice to A, and you have such a map, it's the multiplication. So what happens here is you take these constant, locally constant cosheaves on every stratum, and then you glue them together using the multiplication on A. And it turns out that can be made sense of, and this is the heuristic. So that procedure just works as long as you chose a framing or an orientation to tell you which direction in which to multiply, because we could have multiplied left-right or multiplied right-left, and you might have asked, how do we know which one to choose? So that used, and actually that it was an oriented or framed one manifold. So now what's the answer? So in this case now there's an output. The factorization homology of R with coefficients in A is A. And for the circle, you get Hochschild homology. So that's how this works out in dimension 1. Any questions about dimension 1? Yes?
So your cosheaf is a cosheaf of vector spaces, while the factorization homology is then again an algebra. So is it...
Factorization homology is not an algebra. Factorization homology, so let's say that this was, if this is in V, where V is whatever you want it to be, then this will again be an object in V. And I'll just use this symbol H to mean like if it was chain complexes, the actual chain complex, not the graded abelian group.
Okay, so on R you get A as a vector space out from the construction.
Yes. Yes. Other questions? Okay, so that was real dimension 1. Now let's do complex dimension 1. And here I'll be even more brief. So this was Bellinson and Drinfeld's original motivating example for conformal field theory and applications in geometric representation theory. So in the 90s when they had these ideas, I think it was in the early 90s, they wanted to do conformal field theory in a more geometric rather than algebraic way, as it had been done in the 80s in the vertex operator language. So here X is a curve over C. Let's say it's smooth. And now A, the sort of input which is allowed, could be a vertex or chiral, or in the language of Bellinson and Drinfeld, factorization algebra. These are the sorts of algebraic inputs which are allowed. So now one can define this object and Bellinson and Drinfeld called this the chiral homology. And this was just a new object. It wasn't sort of something that people had considered previously. However, it was related to things that people had considered previously, in that if you took H0 of this, then these were the conformal blocks. AKA correlation functions of the CFT associated to A. So it's the essential algebraic structure of the CFT. The CFT, whatever it is, assigns a vector space to surfaces, and then, given certain operators, you want to calculate their expectation. And that's essentially what you do in field theory. And so there are two parts. There are the vector spaces, and then there are the numbers, expectation. And so this is calculating the vector spaces. But that's just the 0th part, and then potentially there are these higher homology groups, and those were just something new. Okay. So that's all I'll say about that. Now, sticking still with dimension 1, we can consider dimension 1 over a finite field. So again, let X be a curve, say smooth, complete, over a finite field. I won't consider more in the great generality what A might be. I'll just consider that there's an interesting example of A, which is the L-adic cohomology of the classifying space of an algebraic group G. So let's say that this is G is a algebraic group. Maybe semi-simple, simply connected. At least for the purpose of of the theorem I'm about to state. So then there's a construction again that looks rather like what we did in real dimension 1. And then you can consider a given output, which is this factorization homology, and a theorem of Gates, Gorey, and Lurie is that this factorization homology is the L-adic cohomology of the stack of G bundles on X. So this is a really natural thing to study in algebraic geometry. Study, try to classify just what the points of this thing are. What are G bundles on X, or more, try to understand that by understanding what the cohomology of it is. And so that can be calculated by these techniques, and then one can perform like weighted counts of this using the sorts of ideas, the advantages which are listed over there, applied here. So this used the entire sort of factorization homology sort of package of techniques, using a lot of ideas of Bellinson and Drinfeld here also. Okay, so that's all I was going to say about dimension 1. Any questions about dimension 1?
Well, why have you not had tell us anything about Cauchy only at stalks?
Pardon me?
You've only told us about the stalks of the Cauchy.
Uh-huh. Well, I told you what the specialization maps were. That's the essential data. So, right. So if you so the way of thinking about so these things are going to be constructible, meaning that they're locally constant on each of these strata, and then to say what a constructible Cauchy is just to say what the stocks are, and then to say what these specialization maps are for every path. So that's if you can do that, then you should believe that essentially you've nailed down what it has to be. There's a theorem that can be turned into a theorem which says that constructible sheaves on some stratified space Z is equivalent to functors from the exit path category of Z to, if this was in V, to V. So that's a theorem of Lurie. So
a question about this. So suppose you take S1 and you look at this constructible sheaf. So you should also say something with the monodromies happening there, right? So just look at one strata. There's still. I guess,
One could, but it's for an algebra, it's going to be constant.
Okay, so there's none of.
Right. So you could consider a more general object than an algebra, where that's not constant, and then that would be a different algebraic notion.
Is there a version of the Ron space for structured topoi in general, or do you need the topological part?
I don't know how to define it for a general topos. For instance, I think I could define it for a Deligne-Mumford stack, but I don't know how to define it for an Artin stack. I'm skeptical as to whether there's a good definition. All right, so real dimension n. So there'll be a bunch of examples here. So one source of examples come from n-fold loop spaces. Another source of examples come from Lie algebras, or rather, certain types of enveloping algebras of Lie algebras. Another source of examples come from commutative algebras. Another source of examples come from shifted Poisson algebras. And then, lastly, all of these examples are related to one another. Another come from observables, or I'll just say from TQFT. Okay, so we'll start going down this list and we'll see how it goes. So what are the so in each of these cases, X will be an n manifold, and maybe we'll say that it's framed. So in other words, there's an we choose an isomorphism between the trivial rank n bundle and X, and of course most manifolds don't have that, so we'd be limiting ourselves in that case, but we might do that for some of these examples, like this one. Okay, so what would our algebra A here be? So in this case, A might be the n-fold loop space of some space Z, or maybe I'll call it B. So let B be pointed so that we can take its n-fold loop space and consider the n-fold loop space or chains on the n-fold loop space. And so the claim is that from such a thing, we can construct a Cauchy on the RAN space. How's that? Well, let's consider the category of disks where this has objects, finite disjoint unions of Euclidean spaces, and morphisms are open embeddings. So the n-fold loop space of something is an n-disk algebra, which means we can consider compactly supported, there's a functor of compactly supportive maps to B. mapping to spaces. Where compactly supported maps, that little c indicates that those are those maps that outside of a compact subset send everything to the base point. So map C of UB sits inside, well, I'll say that those maps such that there exists some k inside of U compact such that f restricted to U minus k is equal to the chosen base point of B. So if you evaluate this compactly supported maps Rn to B, well, this is equivalent to the n-fold loop space of B. And it sends, note that it sends disjoint unions to products. So there's a functor here. Let me restrict to the category which is surjections on pi 0. I'll just put that right there, where you just forget the disks were embedded in X. So this is a category consisting of disks, embeddings between them, compatible with a fixed embedding into X. This thing right here is equivalent to the exit path category of the RAND space of X. That's a theorem that of David and myself with Hirolee Tanaka. And so using this theorem of Jacob-Lurie that functors from the exit path category are the same as constructible co-sheaves, this is how you get your co-sheaf on the RAND space. In the case of, so this is how there's a functor. So this defines a functor, where I'll just say defines a co-sheaf on RAN of X with stalks. Maybe let's say I wanted this to land in chain complexes, so I'll compose with chains also. So with stalks, chains on loop n of X tensored some number of times. So that was, so I just described, but X became B. So I just described how this object right here defines a co-sheaf on the RAND space of X. And likewise, if I wanted this one, then I just wouldn't apply this functor at the end, and it would just be valued in spaces. And here I wouldn't have chains, and it would be Cartesian product. All right, so that's this example. And then you could ask, well, what's factorization homology? This was, I just described the construction. What's factorization homology? So there's a theorem known as non-abelian Poincare duality. Due separately to Paolo Salvatore, Graham Siegel, and Jacob-Lurie, that says that, well, this factorization homology is equivalent to the space of maps from X to B if B is n connective. So there was this condition right here that we needed to impose. And likewise, this procedure is compatible with chains, so if I put the chains version in, I would just get chains on the mapping space. So that's the first sample
Can
calculation.
you explain the map? Or is there a natural direction which always works without the connectivity?
There's a map this way. And it's just, it hits those maps that have support, which can be moved by a homotopy into a disjoint union of Euclidean spaces. And outside of that, it just goes to the point. All right, Lie algebras. Here, there's a thing called the En enveloping algebra of a Lie algebra, which generalizes the usual enveloping algebra for n equals 1. So from this, these objects are n-disk algebras, and a similar procedure allows you to define a Cauchy on the Ron space. And the basic calculation here is that the factorization homology of one of these enveloping algebras is equivalent to the Lie algebra homology of, let's say this was in characteristic 0. Take the compactly supported de Rham cohomology of X with coefficients in G. That has a Lie algebra structure by pointwise Lie bracket on every stalk, and then take the Lie algebra, the Chevrolet complex of that. So that's the basic calculation there. Now, if A is a commutative algebra, this factorization homology is given by the tensor. Commutative algebras or E-infinity algebras are tensored in spaces. And then to address a question from earlier, this is homotopy invariant in X, and it's this tensor. I'll just say for n Poisson algebras, there is no good answer. Rather, you should, Poisson algebra, first you need to quantize it, and then what the calculation is would be some sort of perturbative expansion in the quantization, and has been insufficiently studied. But it's a good thing to think about if anyone is inclined.
That in characteristic 0?
Excuse me?
That in characteristic 0?
Well, if there's no good answer in characteristic 0, I'll stick with that answer in characteristic P.
Makes sense in positive
The question of quantizing an M Poisson algebra to get an En algebra makes sense in all characteristics. But I'm not advertising it in positive characteristic.
So how about the Lie algebra example? That doesn't seem any dependence on n on the right. Is that
On n, that's true. And in fact, it's almost homotopy invariant except for that little c. So the Lie algebra example is a proper homotopy invariant, and the commutative algebra example is a homotopy invariant, and that's not a coincidence. Those two are related by Cazul duality. That duality down at the third one. No one's taken me up on that offer, but it's open.
So for commutative algebras, the right-hand side makes sense, for example, for manifolds without a framing. Is there some...
Oh, yeah. And in fact, that's also true for the Lie algebra one.
But is there like a version of the left-hand side which sort of doesn't need the framing? Or?
For factorization homology, you mean? Definitely. That's right. It doesn't. There's a version that takes as input something that has no framing.
So you probably already said this, but for the commutative algebra example, that's just the commutative ring spectra being tensored over spaces. Is that
exactly? That's what I meant by that tensor right there. So to spell that out in for E-infinity ring spectra, let's say that we consider the sim, E-infinity of V. If this was A, then X tensor A in this case is the E-infinity sim of the suspension spectrum of X with a disjoint base point smashed with A. That.
So we're recovering the THH formula when X is S1.
Yeah. Yes.
You mean V?
Definitely. Other questions? Okay, so now on to the big example here. I would say all of these are which all of these are related to in some way. So if so let's say X is a TQFT. F is a
So I want to take up on your duality statement.
All right.
Algebra.
Which one?
The commutative algebra case.
So in this case, well, I sort of already said it. Duality, in this case, duality says that factorization homology of a commutative algebra is linearly dual, or Spanier-Whitehead dual. It's a factorization homology of a Lie algebra. So the to the extent to which I'm aware of this having been proved is in characteristic 0. So I'm afraid that I should restrict to that one to get that. But then this is just, these expressions look very much the same. Here we have some kind of cohomology of x with coefficients in a certain chain complex. Here we have a homology of x with coefficients in a certain spectrum. This thing right here looks like sim. At the level of associated graded looks like sim with a shift. This is sim with no shift, and so you're looking at Cazul duality. So it says, the duality statement says that those two things are related. That comes up if you, in the for instance, it comes up in, for instance, in this one right here, what was the relevance of this calculation? Well, that was a commutative one, and so to do the calculation of Gates-Gorey and Lurie, it's convenient to switch to the Cazul dual side to actually get their calculation of the Tamagawa number in their paper. So, if you want more details, ask me later.
So there was no good answer for Poisson algebra, but I'm still curious what the Poincare dual story is there.
I only volunteered applications where I gave answers. I mean, it's Poincare this Poincare Cazul duality is, our candidate for like the basic source of duality, and so it would be if the M Poisson algebra was coming from a duality, was arising as observables, as in this example right here, then it would be some new physical duality. Okay, TQFT. So when I say TQFT here, I don't mean in the sense of like a T as axioms. Rather, I mean more like what a physicist would say when he means a topological, he or she means a topological quantum field theory, which has various pieces of structure. One is that you can consider the observables associated to any manifold on which this theory makes sense, and then associated to each observable you try to calculate the expectation of making that observation. So observables can be extended by 0. So they form a covariant functor on opens. So this forms a cosheaf on ran of x, where the stalks being the same thing, tensor powers of I over a configuration of I distinct points. And then, so that's this is put in very different language, and that needs to be combined with a few other results to get this statement, but the good reference for this is this great book by Costello and Glillian, which constructs a large number of examples by perturbative methods. Their book on factorization algebras and quantum field theory. So then you can consider what this factorization homology object is, this homology of the round space. And whatever it is, there's a natural map similar to the one that we saw up there that Stefan asked about. There's a natural map that takes a bunch of locally observables and glues them together to get a global observable. So there's always a map like this. Now this right-hand side is the really interesting object in the theory. You think of the theory as having essentially two parts, as I said, the collection of observables and the expectation that any observable will be observed. And this is now just some new object that we've constructed using a bunch of machinery. And so you might ask, is this an equivalence? And this is an equivalence morally for F perturbative. So in other words, if there was some classical field theory defined as a commutative algebra, and you obtained this quantum theory by sort of adding on a formal parameter and deforming some En algebra type structure over this formal parameter and powers of h bar, where h bar was formal, then that's what we would mean by perturbative. So in other words, it would be something like this example right here as some En algebra deformation of an n Poisson algebra. And if it was that kind of a theory, then this should be an equivalence.
What does it mean, morally?
Excuse me?
What do you mean? Is it morally written in?
I can't hear you.
Did you write? Is it written morally in parentheses?
Morally. I can't tell you what morally means. That's, right, so what you'd want to expect. So morally means that it's not quite true. And I didn't mean that as any sort of reflection on the world that we have it. So let me give you a more precise statement. So if this was a sigma model with affine target constructed as a perturbative quantization, then I could erase morally and say actually. So if it was a sigma model with non-affine target, then there's a modification of this story that sort of works. For a general sigma model which is not perturbatively constructed, then no dice. That's what I mean. Okay, so that's the alpha story. And there are a bunch of applications. There's some great, for this class of perturbative field theories, there are great applications of Kostel and William, like actually constructing these theories and showing that they're well-defined, calculating the partition functions. There are applications for all of these things, and for instance, in calculating the homology of n-fold loop spaces. These sort of recovers results going back to McDuff and Siegel and Bodegheimer, and offers some avenues for computing more general homologies of mapping spaces when the target is not an n-fold suspension as it was in their work. But notice that there were a few restrictions for all of these. So we got some interesting results, but the most interesting results, I would say, were here. For instance, dimension FQ is 1. Here was pretty interesting also. And so you might ask, what about higher dimensional conformal field theory? And I wrote a paper with Dennis Gatescory about that, but we kind of did it wrong. I mean, well, everything we said was right, but we defined a notion of higher dimensional chiral algebras, which was, which we enjoyed and which is interesting, but it doesn't work to capture full higher dimensional conformal field theory or higher dimensional sort of, complex field theory. Not that that was exactly what we were trying to do. So here it was really important that this was 1 here, and also in describing the homology of Bun-G, it was really important there was 1 there. And in describing the homology of this mapping space, it was really important that we had this n connectivity here. And in saying that we were able to sort of get physics out of this, it was really important that this was perturbative here. And so you might ask, can you do all of this stuff can you obtain these same sorts of results without these red restrictions? And so that's what the beta version is all about. Sort of. And the basic idea is that the red restrictions are always going to be there because of how we set this up. Because we put the Ron space right here. And the Ron space is the moduli space of finite subsets. And instead, to do the beta version, we should instead consider more general subsets. Namely, we should just consider more or less arbitrary codimension 1 subsets, namely stratifications. So if you, instead of considering the moduli space of finite subsets, instead the moduli space of stratifications, that's the basis for the beta version, which is this project of David Ayala and mine to use that to pursue some of these same kind of results. So that's what I'll continue with tomorrow. Thank you all very much.
Any further questions?
I mean, complex dimension 1. What is the algebraic input? It's not an E2 algebra, it's something slightly...
It's a vertex algebra, a quasi-conformal vertex algebra, or a chiral algebra, or what Bell and Sintrenfeld call the factorization algebra.
Okay, and that comes from the complex structure you have on your geometry.
Yes, that's right.
Okay.
I might have missed one, but I think all of the...
Could you speak a bit louder, please?
Yeah, sure. I think all of the real examples you gave ended up with constructible co-sheaves on the Rand space.
As per the recipe.
Oh, it's always constructible?
Oh, constructible. No, those are all constructible. The constructible has to do with the T in TQFT. So there are, if one wants to consider quantum field theories, so things which are not topological invariants, then you'd make a few modifications. The essential story is similar.
So do you know of any examples?
Definitely.
The ones that
I would suggest looking at this book of Castro and Golding. There are a rich variety of examples. Look up elliptic complex in their book.
Does it have an index?
Pardon me?
Does it have an index?
Definitely.
Any other questions? I have a question. I have learned recently that you're fond of recollement.
Excuse me?
I have learned recently that you're fond of recollement.
Is that a question?
No.
Oh, okay.
Well, answer this question first. Can you not use it to define the range space of the topos? Did you raise the question yourself during the course?
No, he asked it. I don't see how to define the Rand space of a topos using that. So,
I suggest we thank the speaker.